So we got a new feature here. Figured out how to embed my webcam with the document camera. So this should hopefully help a little bit. It's nice to, kind of be able to learn and looking at me, even though you still can't ask me questions, at least it gives that little bit more of a personal reflection or personal intake. I don't know. It helped me when I used to watch YouTube videos. I always liked the video. So if you don't like my face, cover it up. At least listen to me and let's try this out. So we're going to start another new unit. Now I understand too that the Chatelier stuff is really difficult. I just wanted to get through it before the equilibrium and the kinetics kind of got out of our head. Look, when we get back to school, we'll obviously go through it a little bit more, but at least now you've seen it. So there's a little bit less confusion when we go over it a second time. So we're going to switch gears entirely because that unit really was done. And we're going to talk about nuclear. It's not pronounced nuclear. It is pronounced nuclear. So this is cool. This is one of the most applicable parts of chemistry. Here we are in the modern age with atomic bombs. We live pretty close to a power plant, which is shutting down. Maybe because we'll have a little bit of extra time, we'll look into if power plants are really safe or not. We're going to put that on there. This is a pretty short unit that really comes right out of the reference table. So let's get into it. Okay. Today we're just going to cover the basics of what it means to be radioactive, what it means in the atom, as well as looking outside in the grand scheme of things. So let's just cover the fact of what radioactivity is. So just follow along in your note packet. The definition of radioactivity is when the nucleus gives off particles. There are many different versions of giving off particles, but in a broad spectrum of it, if something is radioactive, the nucleus is emitting something that it really normally wouldn't. So we're going to have stable atoms like carbon 12. That's the majority of the carbon that makes up our food in our bodies. It's not radioactive at all. But then you get something like carbon 14, which is radioactive. Now, that doesn't necessarily mean it's dangerous. Radioactivity is often synonymous with a danger, but really it's just a matter of the nucleus is giving something off. Sometimes it is dangerous, don't get me wrong, but sometimes it's kind of harmless, depending on what the different particle is. So you can see we're going to be talking about what a beta particle is, how it's different from an alpha particle. You already know what a neutron is, but we'll talk about whether that's dangerous or not. Gamma rays and positrons. Those are the 5 different types of particles that can be emitted in radioactivity. So we always start off by talking about, natural radioactivity. Because there are 2 main types. Right now we're going to talk about natural. What do you think the other one is? How about artificial? Right? Artificial. That probably looks like I spelled it wrong. The C is definitely a C and not an E. But natural and artificial. So natural radioactivity takes place around us. That's why it's called natural. It's kind of a good thing to think about, right? You go to the supermarket, you buy something that's natural, you're expecting it to be free of pesticides or GMOs, that sort of thing. It happens in nature. And that's where the word natural comes from. So any element with an atomic number over 83 is going to be unstable. And that's true. Now, there are 92 naturally occurring elements. The first 92 on the periodic table, naturally occurring. The ones that go higher than 92, 93, 94, 95, 96, they're man-made, they're artificial. And as a result, not only do they have an atomic number over 83, so they're going to be unstable, They're also man-made, which kind of gives you an idea that, they're not going to be stable. So the reason why things over 83 are unstable is because at that point, there's pretty much always a disproportion between neutrons and protons. And this nucleus, you got to imagine, right? If a nucleus has an atomic number of 83, it already has 83 protons jammed into it. On top of all the neutrons that it's also going to have, there's going to be a lot of particles packed into a really, really small space. And when you do that, you put a lot of positives next to each other, things kind of start to pop or explode or decompose or transform, which we're going to learn about in a second. So this is the reason why things are radioactive. Just a general thing. And okay, that's kind of a useless thing to write down because I think you've gotten it, but they naturally happen. They're called natural radioactivity because in nature there are certain natural radioactive elements. So one of the definitions that we use is called transmutation. One of the words we use. And basically, this is when one element turns into another as a result of radioactivity. So something happens in the nucleus and the element changes. It gives off some sort of particle and it changes. Now, immediately, I know you're probably thinking, oh, that means it probably lost a proton. It could be, but we're going to get into some of the other situations where it's not necessarily losing a proton that changes the element. So basically, this is just an example of any transmutation. A particle comes flying in, it hits an atom, and out of nowhere, a particle is shot off into the distance. One particle comes in, different particles go out, and we get a new element. So transmutation is a big definition that we're going to be using furthermore, but it kind of just covers all radioactivity when we start with one element and end up with something new. Okay, so let's talk about a couple of different types of decay. I got to check in on this time. So there are a couple of different types of decay. I don't know how many I'm going to get through before this video ends up because I only get 15 minutes to do each one. But let's see. So we have these things called alpha particles. All right. The thing I'm going to ask you to do is to find it on table O. There are two symbols for an alpha particle. So what I normally ask people to do is you find them and write them down. So because I don't have the time to do that, if you want to do it on your own, hit pause, find them, write them in the blank, or just look at the picture that just went flying. But I'm going to show you. All of these particles are going to be found on table O in our reference table. We have the alpha particle, beta, gamma, neutron, proton, positron. All of these symbols, all of these types of decay are listed right here. All right, so what we get is a notation. The notation is how we would, how to write in an equation. So what we're going to do, what we're going to be doing is writing these symbols in equations and showing how it changes the element and determining what element it changes to. So we need to know these symbols, and we need to know that some of these symbols have different notations, but they mean the same thing. And then you have symbols. So you have two things. This is kind of something that you would imagine being said in a sentence. Is this a particle? Or which particle was released in the equation? You'd look at something in the notation. So let's take a look at what an alpha particle is. It basically is a helium atom, right? That's what it is. We look at it as this symbol, or we can look at it as the alpha symbol one way or the other. And what do we know from this? This goes way back to Unit 1 that we talked about. We have a top number and a bottom number. When an alpha particle is emitted from a nucleus, it looks like this. We're looking at a particle that has left the nucleus with a mass of 4. A particle that has left the nucleus with 2 protons. And when you think about that, you're basically saying that this thing, this combination of subatomic particles, shot out of the nucleus. 2 protons and 2 neutrons. Now, before we get too far ahead of ourselves, you can understand how that would change the element. If an alpha particle just disappeared from a nucleus, 2 protons have automatically already been removed. So the nucleus, let's just imagine it had, 95 protons in it. And an alpha particle is removed. It comes from the nucleus and then shoots out an alpha particle. Those 95 protons that were there are now 93. Whatever the mass was before, it's now 4 less. And automatically the element is changed. So this is the first type of particle that can be lost from a nucleus. And something to note, which we're going to get back to, just kind of write it down and go along with it for now. It has the least penetrating power, which means that it's not as dangerous as some of the other ones. As a matter of fact, if somebody was shooting alpha particles at me and I held up a piece of paper, it would stop them. And so that type of radiation is not that dangerous. If a piece of paper can stop it, it can't penetrate the paper. It's not going to affect the inside of my cells, because if it can't get through paper, how's it going to get through my body? Okay, so that's the first type of particle. I would like to, where are we at here? So look at a decay problem and in an equation, and then we'll call it quits here, and I'll make another one for the rest of this. But when we say we're talking about decay, we're talking about radioactive decay. Okay, radioactive decay. The alpha particle is just the particle. 2 protons, mass of 4, 2 protons, 2 neutrons. It's an alpha particle. When you start talking about alpha decay, all you really mean is that there was an alpha particle that it was emitted from a nucleus. So now we're not just talking about the particle, we're talking about the act of radioactivity. So alpha decay is an alpha particle being lost from a nucleus. Okay? So here's an element. It's radioactive. It gives off alpha particles. Just a quick review, because why not? We're at that point anyway. Bottom number is the number of protons. Top number is the mass. Remember, we find the mass by doing protons plus neutrons. So if I wanted to right now, I could ask you to find out how many neutrons there were. You would subtract 88 from 226 and you would get that. But it's not the point of what we're doing right now. What we are doing is I'm telling you that this element is radioactive. It's radioactive where it's going to give off an alpha particle. Okay, so this radium in an equation, right, reactants, products, is going to give this off. The question that you're going to be asked, I gotta keep that covered, is what's left over. All right, so thinking about this logically, we have to say, started with 88 protons.